We all dream about it, right?
Yeah.
Zipping between stars, exploring the galaxy. It feels almost like a human imperative.
It really does. But then you run into physics, specifically Einstein and the cosmic speed limit. Nothing with mass gets past the speed of light, period.
Ah, but almost period. Today we're diving into maybe the most famous loophole, or potential loophole,
Mm-hmm.
the Alcubierre warp drive.
Exactly. Proposed back in '94 by Miguel Alcubierre. And the mind-bending part, it actually fits within general relativity. The math works, theoretically.
Which is stunning. So
Yeah.
how does it square that circle? How do you get apparent faster-than-light travel without, actually breaking the light barrier locally?
Well, the trick is the ship itself never goes faster than light in its immediate vicinity.
Right.
Instead, you create this warp bubble around the ship, and the drive manipulates space-time outside the bubble.
Manipulates how?
It contracts space in front of the ship, pulling your destination closer.
Right.
And it expands space behind the ship, pushing your starting point away. The ship just sits inside this bubble of normal, flat space.
So the space itself moves, carrying the ship along like a surfer on a wave.
That's a great analogy. And inside that bubble, for the crew, smooth sailing.
No feeling of acceleration. No G-forces.
None whatsoever. You're basically stationary relative to the space immediately around you. You're in an inertial frame, even if Alpha Centauri is seemingly rushing towards you at, say, 10 times the speed of light.
Okay, that sounds almost too good to be true. And, well, as anyone who follows this knows, there's a massive hurdle.
Exotic matter.
The stuff of science fiction, it seems. You need material with negative mass, or maybe negative energy density.
Precisely. Something that warps space-time in the exact opposite way that normal matter and energy do. We need a configurable field of this stuff.
And we haven't exactly found heaps of it lying around.
Not even a little bit, as far as we know for sure. And, worse, the initial calculations Alcubierre did, the amount of negative energy needed was, well, absurd.
How absurd.
More mass energy than might exist in the entire observable universe. Just completely impractical.
Right, okay. So, universe-scale energy requirements. How do we get from that down to something even remotely discussable?
A lot of very clever theoretical work, mostly focused on the geometry of the warp field. Think of it like optimizing the shape.
Okay.
Chris Van Den Broek, back in 1989, had a breakthrough. He realized if you made the surface area of the bubble microscopically small.
Tiny on the outside.
Exactly. But kept the internal volume large enough for a ship, the energy requirements plummeted dramatically.
Interesting. So clever geometry. And then Harold White built on that.
He did. Around 2012, Hal White refined the geometry even further. He proposed shapes, like tweaking the thickness of that warp bubble wall that could potentially bring the requirement down from Jupiter-sized masses of exotic matter.
Which is still enormous.
Oh, absolutely.
Okay.
But down to maybe the mass equivalent of the Voyager 1 probe. So around 700 kilograms.
700 kilos of exotic matter, mind you. Still a huge challenge. But
Right.
wow, that's a colossal reduction. He even thought it might be testable.
Yeah, he proposed using a modified Michelson-Morley interferometer to look for tiny transient warp field effects, assuming you could generate them even briefly.
Okay, let's imagine we solve the energy problem. We find the exotic matter. We shape the field perfectly. We still face some pretty terrifying issues, right? Especially on arrival.
Yes. This is where it gets potentially very destructive. The front edge of the warp bubble accumulates particles as it travels interstellar dust, hydrogen atoms, you name it.
Sweeping them up as it goes.
Kind of. And because the bubble is moving faster than light relative to the outside universe, these particles can build up to incredibly high energies.
And when you stop,
When you decelerate, when the bubble dissolves, all that accumulated energy gets released in a focused, forward-facing beam.
a beam of what?
Gamma rays. High-energy particles. Basically, anything directly in front of you at your destination would be obliterated, or at least severely irradiated.
So you arrive instantly, only to sterilize the planet you wanted to visit. Not ideal.
Definitely not. And there's another problem. Control.
How so?
Inside the bubble, you're causally disconnected from the bubble's edge. Light signals can't reach the front of the bubble from inside the ship to steer it, or, say, turn it off.
Meaning you can't steer in real time. or react to an unexpected asteroid.
Correct. You'd have to pre-program the entire journey or maybe have infrastructure waiting at the destination to help decelerate you. The first trip is essentially blind.
And all this space-time manipulation, it inevitably bumps up against time travel paradoxes, doesn't it?
It does raise that possibility. The math suggests warp drives could create closed time-like curves, CTCs, pathways to your own past.
The classic grandfather paradox territory.
But there's a concept called the chronology protection conjecture. Stephen Hawking was a proponent. The idea is that the laws of physics themselves might forbid time travel.
How?
Perhaps quantum effects would kick in, maybe the required negative energy would explode, or a black hole would form, fundamentally preventing the paradox from ever happening. The universe protects its timeline, so to speak.
Fascinating. A sort of built-in safety mechanism. What an incredible journey just discussing the theory. And speaking of journeys, this deep dive is sponsored by embersilk.com. If you're looking to integrate AI or just get smarter about it, Embersilk is the answer for education and integration needs. That's embersilk.com.
It's worth circling back to that core issue, though, the exotic matter. There's actually a tantalizing, if speculative, connection to modern cosmology.
Oh.
An astrophysicist named Jamie Farnes proposed a theory a few years back suggesting dark matter and dark energy, which make up 95% of the universe's energy density, could actually be two aspects of the same phenomenon, a fluid of negative masses.
Negative masses. Like the exotic matter needed for the Alcubierre drive.
Exactly like it, behaving in ways that mirror what the warp drive requires. It's highly theoretical, of course, but
it raises the question, could the key to faster-than-light travel literally be hidden in the 95% of the cosmos we don't understand yet? Is the solution all around us?
It's certainly a provocative thought. It links this far-out propulsion idea back to some of the biggest mysteries in fundamental physics.
A perfect place to leave it for today. Something for all of you to think about.
Definitely food for thought.
Absolutely. Thanks so much for joining us on this deep dive. If you found this fascinating, please do subscribe and maybe leave us a 5-star review. It genuinely helps get these ideas out there.